Good afternoon. My name is Srini Dharmapuri, and I'm from Sanborn Mapping. I'm going to make a presentation on transmission line applications, including vegetation management using UAS-based LiDAR. So before I get into my presentation, a quick rundown on my company. Sanborn has been in the business since 1866, starting with the fire insurance map, first assessment maps. We started doing the ground control survey in 1866. The aerial mapping started in 1966. We started working with the digital orthophotograph since 1988. Aerial LiDAR mapping started in 1999. We were the first early adopters when the large format digital cameras came into the marketplace since 2004. And we have been providing the oblique imagery services since 2012. In terms of the services, we are a 100% mapping company, end-to-end mapping company, starting from data collection involving vertical imagery, oblique imagery, aerial LiDAR, and also the processing of imagery and LiDAR, and finally, related GIS services. One of the important things our company offers is the software applications, primarily the cloud services, portals, and distribution tools. With regard to the resources, we own our own aircrafts. We have 11 aircrafts collecting data across the country. We have 3 large format cameras, 2 Leica terrain mapper LiDAR, and 5 Midas oblique sensors, and all the other related equipment like airborne GPS, IMUs, and Trimble GPS survey equipment, etc. So before I start the presentation, just I want to give you a quick, show you a quick overview of the products. What you are seeing right now is the orthophotograph. On what you are seeing on the top left is the true color orthophotograph, and what you are seeing is the NIR orthophotograph. So the first one shows the red, blue, green, red. The other one is the green, red, and NIR of an electrical system. And the same thing, the same area is captured using the oblique imagery that you can see from a different angle, 2 different angles. What you are seeing, the building, the same building from 2 different angles. And then what you are seeing in this thing, in this screen, is primarily the point cloud for the same area, primarily an electrical transmission line system. This 3 slides are just shown that we capture 3 different types of data, whether it's a vertical data, oblique imagery, or the LiDAR data. Now, with regard to the LiDAR capabilities, we have been using both the large area aircraft system as well as small area drone systems. The presentation is primarily on the UAS-based drone systems, which I will cover in the subsequent slide. Whenever you need a large area transmission infrastructure, then you need to go in for a manned aircraft system data collection. Whereas if you are looking for a small footprint distribution infrastructure, then primarily the UAS-based collection will be more relevant. And with regard to the transmission as well as the distribution lines, whether it is a manned aircraft or unmanned system, normally we can collect easily 30 points per square meter that allows for accurate no-curve assessment. And one of the most important application of the aerial LiDAR or the UAS-based LiDAR studies in the case of transmission and distribution lines are the vegetation clearance or the vegetation management study that I will show you in the subsequent slides. Also, the laser footprints allows for small feature extraction, such as shield wires, guy wires, and insulator, as you can see in this particular slide. So that's the advantage of the LiDAR, whether it is a manned LiDAR or the unmanned, you can really extract even the small features. The reason being, you are getting an extensive or an accurate point, a large point density LiDAR data that is useful for feature extraction. What this slide shows you, always the confusion is, so we have different LiDAR system, aerial LiDAR, mobile LiDAR, static LiDAR, and now the UAS-based LiDAR. So where shall we use? Obviously, there are 2 different things. One is the area of interest. What is the coverage you are going to cover? and what is the density and accuracy you are looking for. So, you know, if you are looking for the very highest accurate, highest point density LiDAR, the static LiDAR, what is shown here is highly useful. But this is primarily useful for a very small area within the buildings and that type of thing. Whereas the mobile LiDAR is primarily for corridor type of analysis, but around a couple of hundred points per square meter you can achieve as a point density. Whereas the UAS based LiDAR is primarily again for a corridor based study for a small area. You can easily get, as I said, hundreds or even a couple of hundred points per square meter density can be achieved. For a larger area, a wide area, then obviously you need to use the aerial manned aircraft system, but the point density will be, will be less, based on the USGS specifications. Currently, either you can have 2 points per square meter or 8 points per square meter, or, even you can go slightly higher depending upon the case. The benefits of UAS are many, which we have seen. So it's a faster mobilization to remote areas, quicker product or faster product generation, time-sensitive projects you can complete quickly, emergency response. One of the most important thing is you can fuse the data with other data. For example, you can collect UAS-based LiDAR, you can collect UAS-based imagery, and then you can combine both the data sets. Thereby, you can derive more information from the combined data set. And one of the other important advantage is the below cloud deck acquisition. And the last thing is obviously it's very cost effective. Now, there are different UAS-based systems are available in the marketplace. I want to sort of put a disclaimer here. This information is constantly changing. This is, I would consider, is more of an approximate, because if you can go into the deeper research, you will see more systems with the better features what I presented here. Normally, the weight is around 1 to 13 kilogram. The range is 400 to 800 meters. Slightly it may go up now as the technology improves. The number of points is 300,000 to 700,000 points per second. And the millimeter to centimeter accuracy range is possible. Power consumption around 8 watts to 80 watts. And the price range, this is again a constantly changing 8K to 250K. Again, please use this as just a pointer. If you want to, go in for a UAS-based LiDAR, then probably you may have to do a deep dive with the various systems that are available in the marketplace. Now, when you do a UAS-based job for a transmission line application, what are the factors to be considered? We consider there are 6 different points. The first one is the UAS LiDAR specification and the accuracy expectation. This is very, very critical before you embark on any UAS-based LiDAR project, especially for the transmission lines. And then the second one is the data acquisition and calibration related issues, data processing specific to transmission/distribution line projects, vegetation management related issues, quality control, and use of data by multiple stakeholders. So let us address each and every point in the subsequent presentation. The first point I mentioned was LiDAR specifications and the accuracy expectations. So what are the things we need to cover under this category is, we need to make sure what is the LiDAR nominal pulse spacing or the point density that is expected, what is the level of processing, what sort of deliverables are expected, the most important thing, what sort of vertical accuracy the client is expecting, and whether we can achieve that accuracy with the equipment that you plan to use. And they're classified to ASPRS, LAS specs. So what are the classes that are needed? Because unlike the general topo applications, the transmission line applications are different because you may need some different classes to be used. So which I will explain in the subsequent slides. And also the project size, whether it is a large area, corridor, etc. And the most important thing is the control point requirements. So these are all related to the specification and the accuracy requirement. And then we need to think about the managing the data. How are we going to process the data, and what are the deliverables that we are going to get out of this data, and what format the data is going to be provided. So these are all the things needs to be worked out even before you start a project using a UAS-based LiDAR. This is the LiDAR data processing workflow, which is predominantly same, whether it is a manned or unmanned system. You start with the project setup, determine the ground control that is needed for the project, then perform the UAS LiDAR collection, then SBIT creation, and then geocoding, spatial constraint, that is where you adjust your point cloud with respect to the control, and then you perform the classification, and then create the derivative products from the LiDAR, and finally you deliver the products to the client. And in between, you see there are series of QA/QC steps are involved, and this each and every step is very critical so that you make sure that the data meets the necessary requirements before it is pushed to the next stage. So the next step in any LiDAR project is the data acquisition and calibration related. So there are a couple of things you need to consider, especially in the case of UAS. As the UAS-based data collection is controlled by FAA, we need to pay attention to the authorizations that are in place, make sure that we are covered on all aspects. And at the time of data collection, make sure to check the surroundings for eye obstacles, the takeoff, the mission, and also the landing. We also need to identify alternate landing locations. We need to pay attention to the possible air traffic. We also need to pay attention to the ground activities. And the most important parameter that we always consider, whether it is an unmanned or unmanned mission, is the weather. Make sure that the data collected during the time will be usable for subsequent data processing. And once you collect the data, you will have a couple of things. One is the base station data and information. That is where you place your GPS, and also the airborne GPS and IMU data. That is one which will be very useful for at the time of creating the SBIT. And the make, model, and the antenna height is important. The lever arm measurements for UAS, that is also important. And finally, the range data that comes out of the LiDAR sensor. So these are all the parameters that you need to pay attention during the data acquisition stage. Once the data acquisition is done, you need to do a quick QA/QC to check for the data coverage to make sure that you have the complete data set before you leave the area. And also, if needed, you may have to make some adjustment to the flight collection parameters where necessary. So based on our experience, I think we have noticed the flight time for each mission is around 20 minutes. Again, I want to caution here, this will change system to system. This is an average number. So and also with the better systems, you will have more time on the air. So this is only an average number. The point density will be somewhere around 100 to 300 points per square meter. In some cases, the client, though they would expect you to collect the data in 100 to 300 points, they would expect you to provide a down-sampled data set. Let us say they would expect, okay, you may collect 300 points, give me only 30 points per square meter or something like that. And this base station requirement is primarily based on our experience. It is 10 kilometers from a base station. But nowadays with a Trimble PPTX, I think in majority of the cases, you can get away from the base station requirement. So that's one of the advantage, you can collect the data without the base station. And finally, the most important thing we need to think about is the absolute accuracy. What sort of absolute accuracy we are going to get with ground control, without ground control, and whether it is in line with the client expectation, that needs to be determined. As far as the data processing is concerned, all the data, whether it's just like the manned system, the UAS-based system also will be stored in the ASPRS LAS format. There are various, as I said, in the case of topographic mapping, we use some standard class like the ground points, buildings, vegetation, etc. But whereas in the case of transmission line, we will be, in addition to the ground points, then these are all some of the classes the client will normally expect you to process, like the wires, poles, wires guard shield, that's a class number 13, wires conductor, that is class number 14, transmission tower, that's a class number 15. And wire structure, that is a wire structure connector, that is a class number 16. So these are all the different classes that will change depending upon the client requirement. But primarily most of the classes are available in the ASPRS classification. So what you are seeing in this slide is the classified point cloud, a topo view or the vertical view of a of a transmission system. And the same data in the point cloud that is viewed in a oblique view. And it is the same thing, again, the data is viewed in a, I would say, in an oblique view for the transmission line system. Now, having classified the data, the next stage of the study will be the vegetation management. What normally the clients expect in the case of vegetation management is, given a transmission tower or the center line, they want to know what sort of vegetation encroachment is there from the center line 25 feet on both the sides. That means using the poles as the center line, you create a buffer that can be 25 feet or 20 feet or 15 feet, and then try to map those vegetations that fall within that buffer. So that is a very critical piece of information the transmission or the distribution companies will be looking for. So in a particular study, what we have been asked to do is, primarily we want to extract the vegetation encroachment at 5 feet level, 10 feet, 15 feet, 25 feet, and 30 feet. And again, these classes, they can be stored in class 41 to 45, not necessarily the same number. You can use any other number that, that ASPRS allows up. I mean, from 0 to 255, you can put any class. So you can use any of the class number for this classification. So this is an example of where the vegetation management is mapped with regard to the transmission line. What you are seeing here is two different views. One is with the imagery, the other one is the vertical view. What you are seeing on the red polygon are those vegetation that needs to be addressed immediately. And the blue one is the one that needs to be handled subsequently. The benefits of vegetation management is, you are able to deploy the resources at the precise location. So naturally the cost savings, strategic application of trimming equipment, clearance around utility lines and overhead conductors. So these are all some of the major benefits of vegetation management. With regard to the QOQC, these are all the parameters we need to see. One is the data density, the data void, completeness of the coverage. If you're going to do create a DEM, the QC of the DEM, and then the vegetation class QC, absolute accuracy, and the metadata validation. These are all the parameters that needs to be QC'd before the data is delivered. With regard to the deliverables, it is a set of classified LAS points at original density. And another set of classified LAS points, as I said earlier, it is a downsamp to delivery. And you can provide a KML or a shapefile of the vegetation encroachment polygons. It can be a 2D shapefile or a 3D shapefile, depending upon the case. And also you can show a KML or a shapefile showing each pole with the pole numbers and pole height. These are all only examples, and each and every transmission line and vegetation, the distribution line project will be different. The requirements will be different. This is only one sample project. I'm giving you an example. And in some other projects, they would like to go for one step further, give a PLS CAD deliverable also. So in summary, I think, any disruption in vegetation management and clearance schedule expose utility infrastructure to risk due to vegetation or other encroachments. So that is one of the very critical thing. So it avoids the vegetation management studies using the UAS-based LiDAR, minimizes or avoids the risk. And also the UAS-based collection is very useful for vegetation management that we have seen in the past. So with the more and more improvement in the UAS-based LiDAR takes place, and we foresee that more and more studies will be conducted, especially on the transmission lines, distribution lines, and also with the vegetation management. And I believe this is my last slide. With that, I open up for any questions